Welcome! In this session, we'll tackle a fascinating problem from LeetCode, problem number 989, add to array form of integer. Together, we'll explore how to approach this problem, step by step, and gain insights into solving it efficiently. Let's get started. In this problem, we are given a non-negative integer represented as an array of digits called number, and an additional integer k. The array form of an integer means that each digit of the number is stored as an individual element in the array, listed in order from the most significant to the least significant digit. For example, the array 1, 2, 0 corresponds to the number 120. Our goal is to add the integer k to the number represented by the array number and return the result in the same array form structure. The input includes number, which is a list of digits between 0 and 9, and k, which is a non-negative integer. The constraints specify that number has no leading zeros, is at least one digit long, and can be very large, with up to 10,000 digits. The integer k is also non-negative and always less than or equal to 10,000. The result of the operation will be a list of integers that represents the sum of the number from number and k in array form. Let's break this down with some examples. In the first example, the input array number is 1, 2, 0, 0, representing the number 1200, and k is 34. When we add these together, 1200 plus 34 equals 1234. The output is 1, 2, 3, 4, which is the array form representation of the sum. This shows that we are essentially performing addition in a way that maintains the array form structure for the result. Here's another example to illustrate the concept further. If the input array number is 2, 7, 4, it represents the integer 274, and k is 181. When we add 274 and 181, we get 455. The output is 4, 5, 5, which is the array form of the resulting sum. In yet another example, when number is 2, 1, 5, representing the integer 215, and k is 806, we perform the addition 215 plus 806. Let's now see what the result of this operation looks like. The output for the previous example is 1, 0, 2, 1. This is because 215 plus 806 equals 1021, and the array 1, 0, 2, 1 is the array form representation of the integer 1021. The problem also provides several constraints to keep in mind. For example, the length of number can be as large as 10,000 digits, and each element in the number array is a valid digit between 0 and 9. Additionally, number will not have leading zeros unless it is the single-digit number 0. The integer k is always non-negative and capped at 10,000. When solving this problem, it's important to consider edge cases. For instance, if number is 0 and k is 0, the output is simply 0. If number is 9 and k is 1, we see carry propagation, resulting in the output 1, 0. Another example of carry propagation occurs when number is 9, 9, 9, and k is 1, where the output becomes 1, 0, 0, 0. For large inputs where the length of number is the maximum allowed, such as 10,000 digits, and k is 1, we must ensure our solution handles this efficiently. Finally, when k is 0, like in the example where number is 1, 2, 3, the output remains 1, 2, 3, since no addition is performed. These cases highlight the need for an approach that seamlessly handles both regular and special scenarios. In this problem, we are tasked with adding an integer k to a number represented as an array of its digits, known as the array form of the number. For example, if the array is 1, 2, 3, and k is 912, the result would be 1, 0, 3, 5, because 123 plus 912 equals 1035. The key here is that the array represents the number in its most significant digit first order, meaning the leftmost digit is the highest place value. To solve this, we need to add k to this array representation just as if we were performing manual addition in base 10, starting from the least significant digit on the right. A critical aspect of this process is handling carry values, which can propagate across multiple digits. Additionally, since k may have more digits than the array, we have to account for cases where the result's length exceeds the original array. While it might seem tempting to directly convert the array to an integer, add k, and then convert the result back to an array, this approach could become inefficient or impractical for very large inputs. So, we'll need a more robust strategy. Several approaches can be considered to tackle this problem. The first is the brute force approach, which involves directly converting the array to an integer, performing the addition, and then converting the result back to an array. For example, you could join the digits of the array into a string, convert it to an integer, add k, and then split the resulting number back into its individual digits. While this approach is simple and easy to implement, it has limitations. Converting the array and the result to and from integers has a time complexity of O(n), where n is the length of the array. More importantly, this method can fail for extremely large numbers in languages that impose limits on integer size, leading to overflow issues. A more efficient and scalable approach is to perform the addition manually, digit by digit. This method mimics how you would add numbers on paper, starting from the rightmost digit, adding the digits along with the carry, and propagating the carry as needed. By iterating from the least significant digit, you can directly manipulate the array without the need for conversion. The digit-by-digit addition approach has a time complexity of O max n log k, where n is the length of the array and log k represents the number of digits in k. This is because we process each digit of the larger of the two numbers, either the array or k. This method is highly efficient for large inputs due to its simplicity and reliance on basic arithmetic operations, avoiding any costly conversions. It also eliminates the risk of integer overflow, making it a robust choice. The chosen solution for this problem is the optimized approach based on manual digit-by-digit addition. This strategy is more scalable and efficient than the brute force method because it directly manipulates the array and handles carry propagation seamlessly. By avoiding unnecessary conversions, this approach is better suited for competitive programming scenarios and real-world applications where input sizes can become very large. Each approach has its own trade-offs. While the brute force method is straightforward to implement and works well for small inputs, it is not suitable for large-scale problems due to its inefficiency and potential overflow issues. On the other hand, the optimized approach introduces a bit more complexity in terms of implementation but provides significant benefits in terms of efficiency, scalability, and robustness. This makes it ideal for handling very large inputs where the brute force method would fail. Overall, the optimized approach strikes the right balance between simplicity and performance. By focusing on digit-by-digit addition, it avoids unnecessary overhead and ensures that the solution can handle even the most challenging scenarios gracefully. With this, we have an efficient and elegant solution to the problem. To start, let's break down the problem. We are given a number represented as an array, where each element corresponds to a single digit of the number. For example, the array 1, 2, 3 represents the number 123. Alongside this, we also have an integer k, and our goal is to add k to the number represented by the array and return the result, again as an array of digits. For instance, adding 912 to 123 gives us 1035, which we would return as 1035. The algorithm begins with initializing an empty list called result to store the digits of the sum as we compute them. We also initialize a variable carry to the value of k. This variable will help us manage the addition process digit by digit. Since addition begins with the least significant digit, we process the array number from right to left. During each step, we calculate the sum of the current digit from number and the least significant digit of carry. This is achieved by using the modulus operator on carry. After updating the carry to remove its least significant digit, we append the current sum's digit to the result. This process ensures that all digits are added systematically, even if k is longer than number. Once all the digits in the array have been processed, we need to check if there is any remaining carry. If the carry is greater than 0, it means there are still digits left to be added. In this case, we continue extracting the digits of carry by repeatedly taking its modulus by 10 and appending the result to the result list. Each time, we divide the carry by 10 to remove the least significant digit. At this point, the result list contains the digits of the sum, but in reverse order, because we appended the least significant digits first. To produce the correct sequence, we reverse the result list. Finally, this reversed list is returned as the output, representing the sum of the number and k as an array of digits. The key to this algorithm lies in its simplicity and efficiency. By iterating through the array number while simultaneously managing the digits of k through the carry, we effectively handle the addition even when the numbers have differing lengths. The carry mechanism ensures that the addition propagates correctly across all digits, no matter how large k is compared to number. Processing the digits from right to left aligns with how we traditionally perform addition manually, starting with the least significant digits first. In terms of data structures, we use a list, result, to store the digits of the sum during computation. This list is reversed at the end to produce the correct order. The integer carry is crucial for storing the intermediate results of the addition, including any remaining value of k that hasn't yet been processed. Together, these components allow the algorithm to handle the addition efficiently and correctly. In solving this problem, we must also account for several edge cases. First, if the input array number is empty, we treat it as representing the number 0. For example, if number is an empty array and k is 5, the result should simply be 5. Next, if k has more digits than number, such as when number is 1, 2, and k is 9999, the algorithm must ensure that all digits of k are included in the final result. Additionally, the result should never contain leading zeros. For instance, if number is 0, 0, 1, and k is 99, the output must be 1, 0, 0, not 0, 1, 0, 0. Lastly, we must handle cases where the carry introduces an additional digit to the sum. For instance, adding 1 to 999 results in 1, 0, 0, 0, as the carry propagates through all digits and creates a new most significant digit. Regarding complexity, the time complexity of the algorithm is O, max, n, log 10, k, where n is the number of digits in number and log 10, k, is the number of digits in k. This is because we iterate through the digits of both numbers. The space complexity is also O, max, n, log 10, k, as the result list stores at most one additional digit beyond the longer of the two inputs. Let's walk through an example to solidify our understanding. Suppose number is 1, 2, 3, and k is 912. We start by initializing result as an empty list and setting carry to 912. Now, we process the digits of number in reverse order. First, we add the last digit of number, which is 3, to the least significant digit of carry, which is 912% 10 or 2. This gives us 5. We append 5 to result and update carry by dividing it by 10, making it 91. Next, we add the second to last digit of number, 2, to 91% 10, which is 1. This gives us 3. We append 3 to result and update carry to 9. Finally, we add the first digit of number, 1, to 9% 10, which is 9. This gives us 10. We append 0 to result and update carry to 0. At this point, we check if any carry remains. Since carry is now 1, we append it to result. The result list is now 5, 3, 0, 1. Reversing this list gives us 1, 0, 3, 5, which is the final output. Thus, the sum of 123 and 912 is correctly represented as 1, 0, 3, 5. This solution to LeetCode problem 989, add to array form of integer, is implemented to handle the addition of an integer k to a number represented as an array of digits, number. Here's a step-by-step explanation of the code. 1. Initialization. The function initializes an empty list result to store the digits of the sum in reverse order. A variable carry is set to k, which will help in performing the addition digit by digit. 2. Iterating through the array, the function processes the array number from the least significant digit, rightmost, to the most significant digit, leftmost. This ensures that additions are handled correctly, propagating any carry to the next significant digit. For each digit in number, the function adds it to carry. The last digit of the resulting sum, carry %10, is appended to the result list. The carry is updated by performing integer division by 10, effectively removing the last digit. 3. Handling remaining carry. After processing all digits in number, there might still be a non-zero carry, e.g., if k is larger than the number represented by number. While carry 0, the function continues extracting digits from carry and appending them to result. 4. Reversing the result. Since the digits were appended to result in reverse order, starting from the least significant digit, the function reverses the result list before returning it. This ensures the output is in the correct order. This implementation is efficient, with a time complexity of O, max, n, log, k, where n is the length of number and log, k, represents the number of digits in k. The extra space used is proportional to the size of the result, which depends on the larger of the two inputs, number or k. Edge cases, such as number being empty, k being 0, or very large values of k, are handled naturally by this implementation due to its digit-by-digit processing and carry propagation. This is the Java implementation of the add to array form of integer problem, mirroring the logic of the Python solution. The code uses an array list to dynamically store the digits of the result while iterating through the input array in reverse. Carryover logic is applied to handle additions exceeding a single digit. Finally, the result is reversed before returning it, as the digits are appended in reverse order during calculation. Key differences from Python include explicit type declarations and the use of Java's collections utility to reverse the list. Here, we start with the first example where the input array is number equals 1, 2, 0, 0, and k equals 34. To solve this, we initialize an empty list result to store the result digits and set carry to the value of k, which is 34. The process involves iterating through the digits of number from the rightmost position. Starting with I equals 3, the value at number 3 is 0. Adding this to the carry gives us 34. We then extract the last digit of 34, which is 4, and append it to result. This makes result equals 4. Next, we update the carry by performing integer division of 34 by 10, which results in carry equals 3. Moving to I equals 2, the value at number 2 is again 0. Adding this to the carry gives us 3. The last digit of 3 is 3, so we append it to result, resulting in result equals 4, 3. We update the carry again, and since 3 divided by 10 is 0, carry now becomes 0, completing the processing of these digits. Next, we handle the remaining digits of number. For I equals 1, the value at number 1 is 2. Adding this to the carry, which is currently 0, gives us 2. The last digit of 2 is 2, so we append it to result, making result equals 4, 3, 2. Updating the carry by dividing 2 by 10 yields carry equals 0. Finally, for I equals 0, the value at number 0 is 1. Adding this to the carry gives us 1. The last digit of 1 is 1, so we append it to result, resulting in result equals 4, 3, 2, 1. The carry remains 0 after updating. At this point, all digits of number have been processed, and the carry is also 0. The final step is to reverse the result, which is currently in reverse order due to the backward processing. Reversing result gives 1, 2, 3, 4, which is the final output for this example. In the second example, we are given number equals 2, 7, 4, and k equals 181. The initial setup involves creating an empty result list and setting carry to k, which is 181. Starting from the last digit, at I equals 2, the value of number 2 is 4. Adding this to carry gives 185. We extract the last digit, which is 5, and append it to result, resulting in result equals 5. Updating the carry by performing integer division of 185 by 10 gives carry equals 18. Next, at I equals 1, the value of number 1 is 7. Adding this to carry gives 25. The last digit of 25 is 5, so we append it to result, resulting in result equals 5, 5. We then update the carry, and dividing 25 by 10 gives carry equals 2. For the final digit in number, at I equals 0, the value of number 0 is 2. Adding this to carry, which is currently 2, gives 4. The last digit of 4 is 4, so we append it to result, making result equals 5, 5, 4. Updating the carry by dividing 4 by 10 results in 0. With no remaining digits in number and the carry also being 0, the processing is complete. The last step involves reversing the result, which is currently in reverse order. Reversing result gives 4, 5, 5. This becomes the final output for this example. In the third example, we have number equals 9, 9, 9, 9, and k equals 1. After initializing an empty result list and setting carry to k, which is 1, we process the digits from right to left. At I equals 3, the value of number 3 is 9. Adding this to carry gives 10. The last digit of 10 is 0, so we append it to result, making result equals 0. Updating the carry by dividing 10 by 10 gives carry equals 1. For I equals 2, the value of number 2 is also 9. Adding this to carry gives 10 again. The last digit is 0, so we append it to result, resulting in result equals 0, 0. Updating the carry gives carry equals 1 again, and we move to the next digit. At I equals 1, the value of number 1 is 9. Adding this to carry gives 10. The last digit of 10 is 0, so we append it to result, making result equals 0, 0, 0. Updating the carry gives carry equals 1. Finally, at I equals 0, the value of number 0 is 9. Adding this to carry gives 10. The last digit of 10 is again 0, so we append it to result, resulting in result equals 0, 0, 0, 0. The carry remains 1 after updating. Since there are no more digits to process, we append the remaining carry, which is 1, to the result. This gives result equals 0, 0, 0, 0, 1. Reversing the result gives 1, 0, 0, 0, 0, which is the final output for this example. The time complexity of the add to array form function can be understood as O max n log k, where n is the length of the input array number, and log k represents the number of digits in the integer k. Here's why: the function iterates through the array number in reverse order, which takes O n time. During this iteration, the carry variable is updated by adding the current digit, and the last digit of the result is appended to the output list. Since these operations happen in constant time, they contribute O1 per iteration. Once the array is fully processed, any remaining carry is handled in a separate while loop. The number of iterations in this loop depends on the number of digits in carry, which is proportional to log k, because carry starts as k and is divided by 10 repeatedly. Therefore, the overall time complexity depends on the larger of these two terms, resulting in O max n log k. The space complexity of the add to array form function is also O max n log k. This is primarily because of the result list, which stores the digits of the final sum. The size of this list is proportional to the greater of two values, the length of the input array number, which is n, and the number of digits in the integer carry, or k, which is proportional to log k. The input array number and the integer k themselves do not contribute additional space beyond their initial memory allocation, as they are provided as inputs. Temporary variables like carry and loop indices consume constant space, i.e., O1. Combining these factors, the overall space complexity is determined by the size of the result list, making it O max n log k. When comparing this approach to a naive solution, the differences become clear. A naive approach would involve converting the array number into an integer, adding k, and then converting the sum back into an array. While this method has the same theoretical complexities, the conversion steps introduce inefficiencies. Specifically, the time complexity of converting the array to an integer is O n, adding the integers is O log k, and converting the result back to an array adds another O log result, where result is the sum. In the worst case, these steps still lead to O max n log k time complexity. Similarly, the space complexity of the naive approach involves additional memory for the intermediate integer representation, making it O max n log k as well. In contrast, the optimized approach avoids these conversions entirely by directly processing the array in k, achieving the same theoretical bounds but reducing overhead significantly in practice. In terms of case analysis, the best case occurs when k is 0. Here, the function only needs to process the array number, and the while loop for carry is skipped entirely. This results in a time complexity of O n and a space complexity of O n. In the worst case, when k has many digits, such as when k equals 10 m, the function must process both the array number and the digits of k. This leads to a time complexity of O max n log k, and a space complexity of O max n log k. The average case is quite similar to the worst case, as the runtime depends on the lengths of both number and k. To mathematically validate the time complexity, iterating over the array number contributes O n, while processing the digits of k adds O log k. Combining these gives O max n log k. Similarly, the space complexity is proportional to the total number of digits in the result, which is at most max n log k, confirming the space complexity is O max n log k. When solving this problem, there are several common mistakes to watch out for. First, incorrect carry handling is a frequent issue. If you don't properly account for the carry when a sum exceeds 9, the result will be incorrect. For example, adding 2 to the array 1, 9, 9 might produce 1, 9, 11 instead of the correct 2, 0, 1. Another mistake is directly modifying the input array number. This can lead to unexpected behavior if the array is needed elsewhere in the program. Additionally, edge cases involving leading zeros are often mishandled. For instance, adding 5 to 0, 0, 1 should result in 6, not 0, 0, 6. Overflow errors can also occur if you use standard integer arithmetic to some very large numbers, like when number represents 10^100, which exceeds the limits of most integer types. Lastly, relying on inefficient methods, such as reversing the array for digit-by-digit addition, can introduce unnecessary computational overhead, especially when dealing with large inputs. This problem is designed to test your ability to simulate low-level operations, like adding numbers digit by digit. Such simulations are common in computational problem solving and are a valuable skill to demonstrate in interviews. Additionally, you should be prepared to handle edge cases effectively. For example, consider scenarios where the input array number is empty, or k is 0, or where there's a significant difference in magnitude between number and k. Another common discussion point in interviews is space optimization. You might be asked whether you can modify the input array directly instead of creating a new one, and to explain the trade-offs involved. Interviewers may also explore follow-up variations, such as subtracting k instead of adding it, or performing the operation in a different base, like base 2 or base 16, instead of base 10. Being ready for these variations will showcase your ability to adapt the solution to different scenarios. This problem shares similarities with other related problems that you might encounter. For example, LeetCode 67, add binary, involves summing two binary numbers represented as strings. LeetCode 2, add two numbers, deals with adding numbers represented as linked lists, where each node contains a single digit. Another related problem, LeetCode 415, add strings, focuses on summing two non-negative integers represented as strings without converting them to integers. These problems all revolve around the idea of simulating addition at a granular level and handling edge cases like carrying over digits. Understanding this broader context not only helps you recognize patterns but also prepares you to tackle variations of the problem in interviews or other coding challenges. There are several alternative approaches to solving this problem, each with its own trade-offs. One option is the reverse nadd method, where you reverse the input array, add k digit by digit, and then reverse the result. This approach is straightforward to implement but requires additional space for reversing. Another technique involves modifying the input array in place. Starting from the last digit, you add k while tracking the carry, updating the array directly. This saves space but can be challenging to debug. A simpler, though less efficient, method is to convert the array number into a string, concatenate it with k, and convert the result back to an integer, then to an array. While easy to implement, this method struggles with very large numbers. The most efficient approach is to simulate the addition purely mathematically, traversing number from right to left, adding k, and updating the carry as needed. This minimizes space usage and is computationally efficient, but it requires careful attention to detail when managing indices and carry propagation. Great job! We've successfully tackled the add to array form of integer problem. Remember the key insights from this session: handling large numbers in array form, working from least to most significant digits, and managing carry propagation. Thanks for following along, and don't forget to like and subscribe for more problem-solving tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!